Well, good news for as far as series go is sometimes they'll ask us to do these Maclaurin series, and the good news about Maclaurin series is Maclaurin series are Taylor series, but they're centered at 0. Okay, so that's what a Maclaurin series is, and so here's what the Maclaurin series looks like. It's f of x equals summation n equals 0 to infinity, the nth derivative at a, but like I said, it's always, for Maclaurin series, it's centered at 0. That's a given. And so it'd be the nth derivative at 0 divided by n factorial. And then since a is 0, this part also of the Taylor series simplifies because Taylor series is x minus a is 0, so it's just x minus 0 or x to the nth power. So that's the Maclaurin series for f of x. That's the formula. So that is a little bit simpler, not a whole lot. The process is basically the same, but okay. So let's look at a few. All right. So let's find the Maclaurin series for f of x equals e to the x. So again, same process, like I said, we need to come up with that formula, if you will, that expression. And so we'll just start over here with some derivatives, and this is a real easy one. The first derivative is e to the x. Second derivative is e to the x. All right, yeah. So this is about the easiest one you can get. All right, so now, since we're centering it at 0, that's where Maclaurin series are always. We evaluate these at x is 0 or a equals 0. And of course, that's even going to be even nicer. 1. All right? For the f of 0, f prime of 0 is 1. F double prime of 0 is 1. So what's the nth derivative at 0? I believe that'd be 1. Okay. No fluctuation there. All right, so that would mean, yeah, e to the x then would equal, in Maclaurin series, n equals 0 to infinity. The nth derivative at 0 is 1. N factorial over n factorial times x d. So that would be e to the x, basically centered at 0. So yeah, that's definitely different from our previous 1 over 1 minus x. That's e to the x. That's a totally different function there. All right. Let's see. What's going on here? Just gonna see. I think we can't remember. There we go. Yeah, this radius convergence is infinity too, so I'm not going to worry about that one. Okay. Now, so those are like that, pretty much straightforward. Now, like I said, we get a couple of these Maclaurin series for the trig functions. So let me do well, let me do this one, then I'll do that one. So what's the Maclaurin series for f of x equals e to the x over 3? Well, that first derivative of that would be, again, that's going to be our chain rule, isn't it? Be e to the x over 3 times the derivative of the power, which would be 1/3. So 1/3 e to the x over 3. Second derivative will be 1/3 e to the x over 3 times, again, another 1/3. So it'll be 1/9 e to the x over 3. 1/3 times 1/3. Third derivative would be 1/9 e to the x over 3 times another third, so that's 1/27. I think we got the, may need to do a couple more, but I think we've seen this before. So yeah, evaluate these at x equals 0 then for Maclaurin series. So f of 0 would be e to 0 over 3, that'd be just 1. The first derivative at 0 would be 1/3 times 1, so it'd be 1/3. Second derivative at 0, 1/9 e to 0, so that'd be 1/9. And the third derivative is 1/27. So what would be the nth derivative at 0? One over a power 3, isn't it? Now is it the nth power? Yeah, because n equals 1, the first derivative is n equals 1, so that would be 3 to 1. Second derivative is n equal 2, and that is 3 squared, so 3 to the n. So in that case, we've got e to the x over 3 then would be Taylor series, n equals 0 to infinity. The nth derivative at 0 is 1 over 3 to the n divided by n factorial times x to the n. So just to clean it up, that would be n equals 0 to infinity, 1 over 3 to the n times n factorial over x to the n. They might, yeah, this might be one where they would go ahead and combine those. Again, both of those are to the nth power, so they might write that as x over 3 to the nth. Either one I'm okay with, but all right. Good with that? All right, so yeah, let's tackle the sign, because it does get a little bit tricky, the sine and the cosine one. So let's find the Maclaurin series for f of x equals sine of x. Okay, so f of x, sine of x, and we're going to cycle through some sines and cosines here, aren't we? The derivative of sine of x is cosine of x. The second derivative would be negative sine of x. Third derivative would be negative cosine of x. The fourth derivative would be, well, the derivative of cosine is negative sine, so I have a negative sine, so that would be positive sine of x. And then, obviously, we're going to cycle here because we're back to cosine of x, which is just what we went through, right? Sine of x, cosine of x, minus sine of x, negative cosine of x. That's what next four would be the same cycle, right? We'll have the same cycle there. Now, since we're doing the Maclaurin series, evaluate this at x equals 0. So f of 0 is 0. F of prime of 0, because that'd be sine of 0, and then cosine of 0 is 1. Second derivative at 0 is negative sine of 0, which is 0. And then the third derivative at 0 is negative cosine of 0, so that's negative 1. Fourth derivative at 0 would be sine of 0, so we're back to 0. Fifth derivative at 0 is cosine of 0, which is 1. Okay, so the nth derivative at 0. Well, it's complicated because we've got intermingled here zeros and ones and negative ones. Okay, there's not as showing there specifically right now an nth derivative at 0 with those all showing. So here's what we can do on this one. But there is some obvious patterns here because we've got 0, 1, 0, negative 1, and then the cycle will go again. So instead of putting that in, okay, so sine of x, this Maclaurin series, I can't really get that nth derivative at 0 as of yet anyway, over n factorial times x to the n. So I can't come up with this very easily anyway, but there is a way we will regroup here in a way. So let's go ahead and just write out these term by term, because you know, if we do the f of 0 at 0 over 0 factorial times x to the 0, and then the first derivative at 0 over 1 factorial times x to 1, just write out term by term. And then I think we can maybe see a pattern going on here. Don't know how many it'll take, but let's just do a few of them. Well, like I said, that's just, right here, that's just f of 0. So that's 0 over 0 factorial, which is 1 times 1. First derivative is, in this case, is cosine of 0, but it's 1. So that's 1 over 1 factorial times x to the 1. The second derivative at 0 is 0. So we're going to get a lot of terms here that drop out, aren't they? All the even terms are going to drop out because we've got 0 in them. Third derivative is negative 1. We didn't compute it, but by the cycle here, oh yeah, we did. The fourth derivative is 0. And then we're back to 1 on the fifth term. It'll be over 5 factorial times x to the fifth. Okay, so on. So all these even terms are zeroed out. And so what I'm left with is 1 over 1 factorial x to the 1 plus, minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. What would be the next one? Minus 1 over 7 factorial x to the seventh. And then so on. Yeah, I'm just getting those odd terms, if you will. Well, here's how we can regroup. That's what I was saying. We're going to kind of regroup here and write this as a summation. And we are going to do n equals 0. We are going to start at n equals 0. We're just going to kind of reboot our summation here. Well, again, if I start at n equals 0, and I believe that's what they have in the book here, yeah, equals 0. To get that first term to match up, well, I would need that to be n plus 1, wouldn't I? I'm sorry, the top's always 1. The bottom needs to be, to match n equals, it would be n plus 1. However, n plus 1 would not work for that term, because that's the second term, and it's 3. The third term is 5, which would be n equals 2. So n plus 1 is not going to work. It would work for this term, but not for the rest of them. You see what I'm saying? No, to get just odd numbers out of when you're using integers, you use the expression 2n plus 1. There's other alternatives, but 2n plus, if you're plugging in n to be integers and you want them to be odd, that's the expression. That gives you odd numbers. Because n equals 0 gives you an odd number, n equals 1 gives you an odd number, n equals 2 gives you an odd number. You see what I'm saying? If you want even numbers, just a hint, because that'll come up, I think, in one of the homework. That's just 2n, right? That'll give you even numbers if you plug in n equals 0, 1, 2, 3. Okay? All right, but anyway, we want odd numbers, so it's 2n plus 1. So that's going to be, it's going to be 2n plus 1 factorial times x to the 2n plus 1. That would work. Oh, and then what about the alternating? It's alternating signs too. So I'd also need a negative 1 to the nth power, you know. Yeah, because the first term's positive. Second term, which would be n equals 1, is negative. So we start at n equals. Good with that? Yep. Like I said, those sines and cosines, they're a little different. You just have to write out those term by terms and then see. For cosines, I'll just let you know. For cosines, the even ones stay, the odd ones drop out. But is that okay? Any thoughts or concerns there? All right, stop. Yeah.